Hi everybody, we'll continue with 3.5. Now 3.5, the easier part of it is you've done differentiation rules and the chain rule. So here you just apply it multiple times. So if you're asked for the first derivative, you follow the rules. Then if you're asked for the second derivative, then you start with your result from the first derivative and you differentiate following the same thing. So because of that, not many examples will be done, and you'll practice through the homework using what you already know. But why do we need second or third derivative? It's the same idea. The second derivative represents the rate of change of that first derivative. So when you're interested in that instantaneous rate of change, and a simple example before we start is a traditional example is if you have a motion of an object, a rocket is launched or something, then that position, let's call it m, with respect, it's a function of time. All right, we can just call it m of t. When you take the first derivative for this, you get the velocity of that object. When you take the second derivative, you get the acceleration of that object. So you see, there is a meaning for these types of high or higher order derivatives, and we need to know how to find them. Likely the process is once we know how to find the first one, we can just do differentiate again to find the second or the third. So here, based on that definition that we used for the quotient, and we transitioned to the using the limits to the derivative as a rate of change to becoming a function itself, then we can similarly do for the second derivative. And here the notations prime, double prime here, and so forth. Or we can use this other definition with d1 and d2, this here, or dy over dx, d to the second there, and x squared. So be familiar with these notations here when they're used to, you know, which one is which, right? So for example, if you have this polynomial, you can differentiate, you find the first one, then you differentiate to get the second one, then you differentiate to get the third one. You see, the second one is the derivative of the first one. With the other notation, if you want the fourth derivative, means you're going to differentiate the third one, and so forth. So as the derivative of function f at a point x measures the rate of change of the function at that point, the second derivative f measures the rate of change of the derivative f prime. And that initial example I gave is a perfect one for it. And you can see more examples here, and how the derivative changes, the first one and the second one, tell us more about the curve itself. All right. So here for this example, if we have we look at this interpretation of the second derivative of the function in economics, if you suppose the consumer price index CPI of an economy is between the years A and B, so T and B, and described by the function I of t. So this blue function I of t and years between A and B. So you can differentiate, and when you compare this derivative with I, you're getting the inflation rate of the economy. So often you hear about the inflation rate, and now you know how it's calculated. So when you want to find the inflation rate of the economy at a given year, so that's how it's being calculated. So the second derivative gives the rate of change for I prime, and it is possible for I prime to be positive and I prime and I second prime or 2 prime to be negative. This, of course, will tell us how the initial curve changes. So this tells us at a year t, the economy is experiencing inflation, but the rate at which CPI is growing is in fact decreasing. So I will explain this a little more when I give you a simple chart to think about I prime and I double prime, and what does this mean, you know, and how the inflation changes on that. So let's wait for the example until this is gets clearer, because without the graphs it's sometimes harder to see. So let's look at this function here. This applied example, and I edited the slide to fit. You have I with this described this way, the years between 0 and 9 gives the CPI. So find the inflation rate at the beginning of 2010. So T is 6 because T0 corresponds to 2004. And show the inflation was moderating or moderate at that time. So if we take I prime, we'll find the first derivative based on the given formula, right? So you do a 3 times 0.2 negative, you get negative 0.6 t squared. And this one will be 2 times 3 is 6, and t becomes 1, t1. So now for the 2010, which is a t equals 6, I prime is that. And let's compare it now with I double prime, which is an I6, just the curve itself. We talked about the rate and the curve itself. So this is the curve itself. You get 164.8. So if you compare I prime with I to get the inflation rate, you get 8.7%. So now, how does that 8.7% changes? You can go into the second derivative and find it. So let's find the second derivative, because it's going to tell us additional information about this inflation rate. We'll find negative 1.2 t plus 6. So now use again the 6 for 2010, and we find it's negative, that's the important part, negative 1.2. So what does that mean? We see that I prime is indeed decreasing. So if we graph this function at t equals 6, and we conclude that the inflation is moderating at that time. And so look at the curve here. So there is a sharp increase for this I at certain places, but it kind of starts to slow down here, right? And what we will talk about this is concave down, and that's the way I will summarize these. And I'll show you the chart for the last example that I'll talk about, and I think this one in the homework is, let's see what number is this, number 10. And to summarize the idea for is we look at first derivative and the second derivative to tell about the curve, how it is changing. So if you have the first derivative positive, like this case here, and you have the second derivative negative, which is here. So if you do the intersection, right? So this is this quadrant here, not really quadrant, but this box here. So you see the curve is concaving down. If the curve is concaving down, it means the curve or the function is increasing while the rate of change is decreasing. It's slowing down. It is still increasing, but it's slowing down. The rate of change, f of x, is decreasing. In this case, the curve is concave down, right? So when you look at this problem here, the derivative, the first one at 6, let's look at it here. The derivative here, I prime of 6 here, is positive. Then we do the second derivative, it's negative, right? And of course we have the graph here, but now you're gonna refer to these 4 pictures. The first one is positive, the second one is negative, it concave down, means it is slowing down. So now we'll answer this number 10. Suppose that P of t represents the population of bacteria at a time t. And suppose the first derivative, or the rate of change of P of t, is positive. Then we calculate the second derivative, which is the rate of change of P prime. Then the population is increasing at a time t, but at a decreasing rate. So is this true or false? So let's clean this up and mark it down. So P prime of t which is that first derivative, whatever the function is called, it's still the first derivative positive. The second derivative is positive as well, right? So now where they intersect, of course, is this picture here. This is what we expect. If that function first derivative is positive and its second derivative is positive as well, so it's concaving up. If it is concaving up, that means it is increasing, the function is increasing, while the rate of change is also increasing. It's picking up steam, it's going up, right? But the rate of change is also increasing. So that makes this statement false, because this statement claims that when this happened and this happened for this bacteria, the population is increasing at a time, so the first one is correct, but at a decreasing rate. It's slowing down. So this statement is false. All right. Yeah, so the video stopped, and now we'll try 2 more examples. Number 5, just similar way, if you had it in the past, something like this, you use the quotient rule. When you use the quotient rule, you get 5 divided by 6x plus 5 squared. Now for the second derivative, you're going to start with that, which means the denominator squared times the derivative of 5, which is the 0. And the derivative of the denominator, but now remember the chain rule, right? And once you get that, just like in 3.3, now we simplify these. And we get negative 60 divided by 6x plus 5 to the third. And these are the steps for it. For number 7, it's just a polynomial. You find the first derivative. Then from it, you derive it, you differentiate it again to find the second derivative. Then you differentiate the second derivative to find the third derivative. That's all. Thank you.